Debate, and here I am starting a series where we're going to be looking at some of the different machine learning models that there are, right? And obviously, over here in this video, we're going to be talking about the multi-layer perceptron. Now, this video isn't largely based on learning. Rather, this video is more to set a benchmark for the later videos to come, and it's more to set the prerequisite information that you might need to understand to actually create these models, right? Now, if anything doesn't really make sense, obviously you can reach out to me via the comment sections, or you can use ChatGPT to break down the code. Or what I highly recommend is watching Mr. Karpathy's Make More series, and I think I will be linking that in the description below as well. A lot of the code and the concepts introduced here in this specific video come from that series. It's a very condensed version of the code introduced over there, right? I'm not going to be focusing as much as to explain what's actually happening. Rather, I'm just going to put it in and expect you guys to know some of the few things. Of course, I'm going to explain, right? But not in as much detail as explaining those videos. So I highly recommend watching that to build up the prerequisite understanding and knowledge needed to actually create these models. Okay, having said that, let's actually start developing. So first of all, I'd like to show you guys the data set that we're actually using, the names.txt over here. This is from Mr. Karpathy's GitHub. I'll also be putting this in the description. So I've downloaded this, put it into a folder. Right. Now it's already on a computer, you guys should download it as well. Now to start the code, you'll basically import a few things. So import torch, import torch.nn, nn. Right. So these are some of the basic imports needed for any code. Right. And now we're actually going to be opening the file itself. So I believe it's saved over here on my computer. Okay, so here's the actual opening of the file. Let's see the first 100 words here. And as you can see, these are the first 100 words, right? Now what we want to do with this is we want to simplify it. We want to put it into, we want to make it available to our for our system. So we have to find some way to actually hinder the data set, probably put it into one line. Well, that's what we're going to try to achieve over here. Well, I'm going to say .join. Okay. Now what this would do, words 2 would basically take all of these names, it would put them inside a line, right? And it would add this dot. What dot split does is that if you have any trailing spaces or unnecessary, indentations, split at the beginning and the end automatically removes them. Though it's not really necessary over here, I just put that as a precaution. Well, now let's look at words 2, and let's look at the first 100. Okay, expected string instance list found. The mistake I did last time was over here I put w.split, and instead it should be w.strip. There are two different Python functions. Strip takes away the indentation at the beginning. Strip takes the indentation at the beginning and it removes them. Split does something completely different. Well, either way, now this is what we have over here. It basically takes all the words, the names that we had before in words. It takes each individual one and it puts them together and adds a dot between them, right? Now, I'm going to paste some code over here, and let's break this down. Now, what's itos? What itos does is that you're taking set of words, so you're looking at what independent characters are there that are being repeated, right? That would be the ABCs, because the names are made from the ABCs, and that'd be the dot. And you make it into a list, and then you sort that list, right? So itos would be, dot A, B, C, D, E, F, G, H, I, J, K, and so on and so forth. Right, now vocab size, as the name refers, is the vocab size, right? How many characters are in a system. Stoy is a dictionary, right? It returns the string, an integer for enumerating itos, right? So you enumerate itos, you would get the integer string, and it will return the integer part of that, right? It stands for string to integer. Simple. After that, you are converting the date. You're converting the words to over here, this line of text, into a real tensor, right? So you're actually doing stoy w. So for each character inside of this long list, you're turning into an integer, you're putting it into a list, and you're turning into a tensor, which has integer type of torch.long, right? Next, you're actually creating the batch, and this is the code that I used. Well, batch size I'll use is 32. This could be any arbitrary number, so can block size. Well, it depends, right? Now, the batch size, this is this function, so ix creates the actual batches, the indexes, which we're going to batch through. So you start from 0 to length of data minus block size. The reason why we minus block size here is because when you look at the full length of the data, when you create sequences of certain block sizes, right? For here it's 8. When you create the sequences of 8, right? The final or maximum index that you can start with would be length of data minus block size, right? And that's why you're creating indexes from between there. Now, the X part actually create these indexes. X part says that for each I inside IX, right, you start at I and you go to I plus block size, right? So pretend the indexes may be 20. So from 20 to 28, you would look at all the numbers between them and you would put them into X and you would stack them, right? That's basically what this code is doing over here. What Y does, it says that after you have these 8 integers, the 9th integer that you have right over there, you look at that integer and you put that inside, right? And as you stack them, they return a certain shape. So now let's look at the shape over here. Suppose you call the function create batch, right? And you say x.shape, and let's look at y.shape. Okay, so it turns out words 2 over here, or ito sorted, right? Okay. Again, words 2. Okay, yeah, there you go. So x has shape 32 by 8, right? So as we said, you have 32 batches, 32 examples, right? You create these indexes over here, right? From 0 to length of data minus block size. So the range of indexes you could choose from. The shape of this would be batch size, so you choose 32 of these indexes. And for each of these indexes, you create a set of 8 numbers. So you have 8 numbers, 8 numbers, 8 numbers, 8 numbers, and that gives you your x. Now let's look at the shape for y. Okay? Now shape of y is just 32 because these are the final points. For each of the 8, you have this final number that you're looking up to. And that's how you create the batch. Actually dive deeper into, now we're actually going to continue to build the model. Now we're going to actually start by developing the weights. So first we're going to create an embedding table. Now this adds depth to the system. For each of the characters, you're basically encoding each one of them, adding more numbers for the system to be able to find patterns, right? So you can call this as torch.random or randin, as used over here. And let's say this should have shape of maybe 27, because you have 27 characters, right? Just to show you guys that, we can over here print itos dot. I can just press vocab size. Right, 27. So you have 27, and you want to each give them a depth of 10. Embedding table. Okay, now we go to W1, the first weight. Right, we're gonna keep this as a two-layer system for simplicity purposes, but obviously you can add more layers and complexity to the model. Well, we're gonna say, because I've looked at the model previously and I've planned it, we're gonna keep the shape as AT to 100, right? And with weights, you always want to, initialize them at a very low value to, decrease the chances of them being saturated, right? Later on, we might look at chiming or batch normalization, and initializations. But for now, this should do. Bias one, capital, call it capital, torch dot random again. Now you want to follow the shape of 100, so I would just put 100 over here. In fact, you can just initialize these as zeros, right? You can initialize these as zeros. Now W2, we will take the 80 by 100 shape we have now, and we want to bring it back down to 27. So you would have torch dot random, right? So you're having a shape of 100 and you want to bring it back down to 27, right? This would be 0.01 again for, because you want to initialize them at a very, very, very small number to reduce saturation. Now bias would be 27. Again, you would initialize these as zeros, right? And now that we have all our parameters, right? We have all our parameters. Yeah, you can basically just put these all into a list. We're not going to be using torch specifically, but later on you guys might see in classes we use something called the nn.parameter. It basically stores it as a parameter later on, but for now this is fine. We say parameters c w1 b1 w2 and b2, right? I made a mistake there. This should be b2. And you can say for p in parameters, p dot requires grad is equals to true. This is very important over here, because if you don't put requires grad is equals to true, when the system goes into gradient descent, it's not going to calculate the gradients for these weights, right? So this is very, very important right over here. To the forward pass itself. Okay, so for the forward pass, first of all, as you remember, we created the create batch. Yes? So you first call the create batch, you actually create the batch. That should be kind of obvious. You create the batch, right? And now you have these x values and you want to train them. You want to train the model to predict the y values from these x, right? So first of all, you would actually pass x into the embedding table. Now let's suppose you call this, EMB, as for stands for embedding, right? And you say EMB.shape. Let's look at the shape. Right, now this might be kind of confusing. What does this mean? 32 8 by 10. Well, I say imagine this as a cube. Let me explain. Imagine in the beginning when we created the first one, you had a 32 by 8 tensor, right? So you have 32 lists. You have a batch size of 32, so 32 examples, and each of them being 8 long, right? Now you added 10 because for each of the individual characters inside of the 8 sequences that you have, for each of those characters, it refers to this embedding table C, and it adds those 10 towards it. Like you could imagine it like this. As you can see, you have 32 by 8 and then by 10, right? The 10 would be the numbers that you would add to the system, those extra numbers that add depth, right? This is what you mean by adding depth. So instead of just taking the individual, string to integer conversion, right? You would instead put these 10 numbers inside that would actually define each individual character. And that's what it's doing over here. Now, obviously, you cannot pass this number over here into our system because, that makes no sense. Our weights are 2D, and you cannot multiply these together, right? So what do? Well, you have to change the shape of EMB, right? Now, suppose you call this H. And then, suppose you say, EMB.view, and you say, okay, so we obviously know we're supposed to multiply from something that has AT in the beginning. So, we'll keep AT, we'll keep AT at the end, and let's put this as -1. Okay, now what might this return? Let's see H.shape. 32 by 80. So what it basically did there is that it took, let's look at it basically took these two numbers and then multiplied them together, right? In fact, the better way to put this would be to say, H is equals to EMB.view, the first part has to be 32, and you can just say -1 there, right? So you would keep the 32 batches same as it is, and it would only alter the back part, the 8 and the 10, right? So this would give you the same result, h dot shape. Perfect. So now you have this tensor 32 by 8 based on the batch that you created, right? Now this is a representation of the data that you're going to put into the system. Now what this basically did over here, if you had to continue imagining it as a cube, is for each of the characters, instead of having the individual string to integer representation, the index, it replaced that index with the 10 defining integers from C, right? So for each character, you have 10 numbers that define it. So 10, 10, 10, 10 times 8 is 80, right? So instead of having a sequence of 8, you would have a sequence of 80 with 10 numbers defining each of the characters within those original 8. Right, so you have 80, 80, 80, 32 times. Perfect. Okay, now you're ready to pass this on into your layers. So let's start with layer 1. You can say H matrix multiply. I hope you guys know what matrix multiplication is, right? Plus the bias, right? And then here what you do is that you have to add this non-linearity, right? The patterns over here in actually creating names, or in English itself, they're not linear patterns, right? They're very irregular. For that reason, you have to introduce non-linearities. For this one specifically, we're going to be looking at tan h. Right? This is the tan h activation function. Right? All of these over here. We're looking at this example specifically. As you can see, this is what you're using over here. So you basically apply this activation function into layer 1. So suppose you just return layer 1 again. Torch already has its built-in tan h function, and you pass in layer 1. Okay. Now let's look at layer 1 dot shape. Okay. Let's look at layer 1 dot shape. Okay, so it has 32 by 100. How did the shape come to be? Well, in the beginning, we had a shape of 32 by 80, right? We had a shape of 32 by 80. And you matrix multiplied this from a shape of 80 by 100, right? So obviously the 80 and the 80 are going to cancel. So this would give you a shape of 32 by 100, right? So now all of these are defined by 100 instead, right? You put this through different weights. Each number is multiplied by different weights, and it gives this new number, right? And you also add the bias to it. Okay. So now you have this layer 1. Now you pass it on to layer 2 after adding the nonlinearity, right? Now to pass it on to layer 2, you can say, layer 1, which has shape of, as you can remember, 32 by 100, and you multiply from 100 by 27. So you're taking that 100 and you want to convert it back to a 27. Okay, so you would matrix multiply with W2, right? And you would add bias 2. Easy. Now, in layer 2, you do not have to add the nonlinearity. The reason for this is simple. Layer 2 isn't necessarily about finding the pattern. Rather, it is about bringing the pattern back down to an understandable level. Right? That does not need nonlinearity. Layers that are dedicated to finding patterns specifically are applied, the nonlinearities are applied to, whereas layers 2, which job is to bring layers 1's results back down to probabilities, does not need that activation function. So you have layer 2 now, and layer 2 shape. Let's look at layer 2 dot shape. Okay, you have 32 by 27. Right, so now you have your results. Right, for each of the 32 batches that we had, you have 27 probabilities. Well, they're not really probabilities yet, but Torch, when we calculate the loss, will automatically turn them into probabilities. So I have 27 probabilities, and it looks like, okay, out of these 27, for each of these individual batches, which one is most likely? Does it match the Y? Right? Now, how does Torch allow you to do that? Well, you use something called cross-site entropy. Right, this F over here, it comes from this over here. Cross entropy is from torsion and then functional, right? So you have F dot cross entropy. You pass layer 2, and you pass Y, because you're comparing it to Y, right? Now you look at the loss, right? Now that's your loss. Now that's basically one forward pass, right? Now after your forward pass, you obviously have to look back at what went wrong, and you have to make those changes, right? Now how do you do that? Well, you can simply put this into a reoccurring sequence, right? So you can say for k in range, let's say 200,000 to start with, right? So for k in range 200,000, so we'll repeat it 200,000 times, right? You go through the forward pass, you calculate the loss. Now what you also have to do is you have to zero the gradients out. What does that mean? Basically, the way that a torch follows the backward is that it accumulates the gradients unless you have to zero them out. So basically, the gradients for the previous forward would be added upon unless you would zero them out, right? So per forward, you have to zero them out so that the next time you add gradients, they're zero, right? So they're simple, right? So the way you do that over here is for p in parameters. You would go through each parameter, and you would say p dot grad is equals to none. Simple. So every time forward pass happens, before you calculate the gradients, they're all zero, right? They're all none. They're nan values. And as you add on to them, that gives you your grade for each individual parameter, right? So for p in parameters, p dot grad is equals to none. So now you have zero at the gradients. Now you need to loss dot backward. Now what this does is for each of the required grad parameters, it would say, okay, how much does this affect the loss value? How do we minimize this? Right. So now once you have all these loss values, you would go for p in parameters, p dot data is equal to learning rate, which I forgot to define over here. Learning rate is basically how fast you want your system to learn, right? You don't want it to be too fast, because then it might miss out the key details, but you don't want it to be too slow. It tells you how much change do you allow the system to take per step, right? Too large, you miss important detail. Too small, it takes too much time. So it really is some fine-tuning that you need to look at when looking at the learning rate. Now, depending on the size of your model, these numbers can change. Okay, so minus equals learning rate because the gradient point towards the way that the loss increases. You want to point towards the opposite direction. That's why you minus. You go the other way, right? Learning rate times p dot grad. Which way does the gradient point? Towards the way that the loss would increase. So you want to go the opposite way. That's what happens over here. Okay, now this is basically your forward pass. Let's have it print the loss dot item. Parameters. I see. I put an S there. I see. So it's going through the system. Has training itself. We got to a loss of 1.737. Now, normally, what you would do here is I would have originally divided the data over here into two parts: the testing and the actual training data. Right? The training data would obviously use for training, and the testing here, after it's all been done, would be used to see whether or not our system is overfitted towards the training data. But I got kind of lazy here, and I did it this way. But yeah, normally speaking, you should be having test data, right? So now we're going to be actually looking at how to sample, how to actually take from the system, how to use the parameters to create tangible results. Okay, so what you would do here is first you want an out, right? So what do you want the system to output? Like you would connect the dots together, and you would introduce something called a context, right? For this case, you would initialize them as a string of zeros. I'll explain this in a bit more detail, but for now, just take a look at this. Okay, so you would say ix maybe is equals to torch.tensor. You would take context, right? Maybe dtype is equal to torch.long. And you would basically pass this into the forward pass with some tweaks. For sure. Okay. EMB IX. Well, obviously, this is just going to be 1, right? Okay. Okay, now instead of calculating the loss, what we're going to do is we're going to calculate something called a softmax. Right? Now, what is a softmax? Basically, let's call this probs. Probs is equals to torch dot softmax on layer 2. Now, it would basically take a look at whatever you have, right? Maybe I should just define this as dim1 just in case. Dim equals to 1. Okay. Is softmax from Torsto? I'm not sure. I think I need to check. Yeah, so this is something you should always do. If you don't know where some certain function is, always look. Okay, so as you can see, it's from torch.nn. So instead of calling torch.softmax, it would be nn.softmax, right? And s is capital here. And s is capital here, right? Dim1. Okay. Okay. I don't know if this is correct or not, but okay. Anyway, and then you would say chosen, right? So basically what softmax does is that given a dim1 just basically says horizontally, right? So because this has basically only shape 1, this has shape 180, 180, right? So because there's only one batch, it would just say across that one batch, that one row, all the 80 numbers, you would convert them into probabilities, or at this point, it's really just 127. So all 27 numbers here should be converted into probabilities, right? So the sum of all these 27 numbers should be 1, right? And that's what softmax does, is that it converts into probabilities. As you can see, probs over here. Now chosen uses something called torch.multinomial. Multinomial applies this softmax to actually make a prediction. Torch.multinomial. Don't go into AI mode. Torch.multinomial. Basically, given the probabilities, you can ask it, at random, which one would you pick? Or which one would you most likely be able to pick? Right? So it's torch.multinomial. To give it the input, we should put it as probs. Number of samples is 1. Replacement, we don't need because we're only taking one sample at a time. And generator none and out none. Okay. So you would basically call probs inside of this, and you would say num samples. Right, num samples, does it have a placement in them? And num samples, yeah, num samples is 1, and you would just call dot item because you only want the item, not the generator itself. Okay, so now you want to end the chosen if you reach a dot, right? Because if you reach the period, you want to say, okay, that's the end of the name, right? There's no more name after that, right? So you would say, first you would say, you would first convert this chosen. First of all, you would say if chosen is equals to, or first I think you would convert it into, right? So you would say itos chosen because you're converting it into the actual string, and you would say, new, let's call it new is equals to itos chosen, and you say if new is equals to this period, you say break. Easy enough. Now what you do is that if chosen is not the new, if chosen is not the new, you would say, context is equals to context from the first place to the rest, right? Plus this new chosen number, right? And that would give you your new context for keep. This would allow the system to keep repeating again and again until it reaches this dot, right? So it would keep calculating new. It would keep looking at it whether or not it's a dot. And you would say here, out dot append new, right? You would say out dot append new, and then final, when it breaks, you would say, print dot join out. Okay. Right. So this is where it went wrong. What went wrong was there, instead of having nn.softmax as this led us to believe, it's actually f.softmax, right? That's the real function. nn.functional.softmax, yeah. So this is the function, right? You give the in and dim. The previous one is just a class. Okay, so you apply f.softmax to layer 2. Dim is 1, so you do it horizontally, right? Multinomial from these line of probabilities chooses 1, right? That's what nominal sample means. And you take out the item, and then you actually convert it into chosen, right? Insert the string. Given this chosen, you would turn it into a string, and you would say, okay, if here of the strings equals the dot, you break. That's it, right? And then you print whatever you have, right? Context would allow the system to reloop again and again and again, right? So basically, with context 1 to whatever it would mean, for example, suppose block size are here. In reality, it's 3, but suppose block size here was, 3. Okay, now what 1 to the rest would mean, you would keep these two, right? You would keep these two, and suppose the new integer has a number 1, right? That would mean it's a. So you would first keep these two, and you would say, okay, so the next integer is a, so you add 1. Right, now suppose the next integer after a is maybe, I don't know, b. So when you have b, you would keep these two, because you're taking index 0, index 1, so 1 to the rest. So you're taking 1 to the rest, and then you're adding that b, which has index 2, and then so on and so forth. So the next term, suppose it's c, right? You would have 1, 2, and then c, which is 3. And then it keeps on going until at some point, I don't know, maybe you have 4, right? Suppose the term right after it, after 2 and 3, had maybe a 0. Now, a 0 here is going to be a dot, right? If the chosen chooses a dot, a 0, then it says, okay, this has to break. We have whatever outs we have, so outs would have 1, 2, and 3, and the dot, and it would print that out. It would print these two out. So that's the basic, sampling loop over here. The forward pass mainly is kept the same. Only the losses changed to actually pick. So let's test it out. Larla. Okay, there we go. Let's ask it to create a bit more. For maybe we should not use k. For m in range, let's generate 100 names. So this, and we can simply just indent. Wait, my bad. And we can simply indent. So there you go. 100 names that actually sound like names. Leyland, Losa, Hirina, Lun, Larissa, Relin. See, these are all names. So it figured out a sort of pattern to actually, develop these names. So now we have the overall structure of the entire system, right? So what we're gonna do now is that I'm gonna keep whatever I have up over here, but I'm going to add a bit of torch into the system. I'll just paste it and I'll explain it. Don't worry. This part I'm going to explain in a bit more detail. Right? So this is going to be our training loop. Let me just put this into a different one. Delete it from here. Okay. And this is our sampling. Okay, I'll explain everything right now. Okay. So first of all, this is a class. If you don't know what a class is, I suggest you look at a few more Python videos online to actually understand the basics of Python, right? Now, you call a class and you say MLP, you call it MLP, and you put in this nn.module. Now, this is very important over here. nn.module allows you to use, the different things that come inside nn.module, right? For example, nn.parameters here and so on and so forth. You have to pass this in to actually create the model class, right? And then you call init, in which you would define, the prerequisites that you would need. Now, because you passed in nn.module, whenever you define your init, you have to pass this, right? You have to pass super.init. This is something you have to do, right? Okay, so now that you have this much, you start initializing your weights. So this much seems, clear because this is the same as what we had before, right? Same as what we had right over here. But then if you look over here, we have, these few extra ones. And this is where I introduce batch normalization. Basically, what batch normalization does is whenever we passed in layer 1 to its torch.tanh, depending on the values that layer 1 has in the beginning or throughout the process, if they vary in values, the system can become way too saturated, right? A lot of neurons go dead, right? And you don't want this saturation. You don't want the neurons to die, right? So to prevent that, you have to sort of scale the inputs that are going into the next layers. So to give an analogy, if you were to imagine a classroom full of students, maybe, each coming from different parts of the world, to effectively analyze them in a proper manner, you would have to find common ground. You would have to convert them all into some sort of common metric to then analyze and further work with. That's kind of what batch norm does. It takes all these different points and it calculates the mean and the variance, right? It normalizes them, and then it uses these two parameters to then alter the scale, right? These are learnable, so it allows the system some space to learn from these parameters, right? So that's what basically batch norm is. More specifically, what it does, that it just normalizes everything, right? It brings them into a standardized set so that everything stays within a certain range and it doesn't explode, right? The largest number and the smallest number don't have a big gap, and that's kind of what batch norm does, is that it allows us to regularize the system. Okay, so here's how it happens. You have your self.gamma, which kind of acts as a weight here, right? It allows us to scale when we actually call the batch norm. And your beta, it's kind of like the bias. Now, what register buffer does here, we actually use this more for when we train. Register buffer means that this running mean value, uh, every time it calculates a new value for running mean, it is stored permanently. It's not restarted. So when you save this model using torch.stateDict, save stateDict, the values of this running mean aren't reset to 0, right? So whenever you go to training, the model automatically knows that running mean has this value, right? This value doesn't change. So this value is gathered up while training, right? It stores this value. That's what register buffer allows us to do. So you initialize these as torch.zeros. Now, why zeros? Because it's the mean, right? Mean can be 0, but variance cannot be 0, right? So you initialize this torch.ones. Okay, now we actually went to the main batch norm part. So you put in X, that's your input, right? From layer 1, that's your input from layer 1 to batch norm, to then normalize, then put it to tanh. So layer 1 outputs goes into batch norm goes into tanh. This one allows the desaturation of tanh over here. Okay, so how does this work? So you first calculate the mean. Dim 0 just basically means along the rows, right? So the mean along each row, each batch, the mean along each batch, variance along each batch, right? Unbiased is about Bessel's correlation. This is more of a variance thing, right? It talks about, if you have sample variance, to get an estimate of the overall total variance, you would divide by n minus 1 instead of n. That's just a bit of statistics here, but we do not need Bessel's correlation over here. So we put unbiased is equals to false. Now moving on, if you're training, right? So while you're training the system, you want to develop the self.running mean and self.running var, so then you can use it when you're not doing the training, right? So here's how it basically works. You have momentum, which is basically, how much do you want it to change per epoch, right? So here we put at 0.1. So 1 minus 0.1 times self.running mean. How much of the previous running mean are you preserving? Plus self-momentum plus times mean. How much of the new mean are you adding to the running mean? So this basically allows the system to create an estimate of, somewhere around of what the mean should be per batch, right? Same with variance. It's the same thing over there. It allows us to calculate an estimate of what the mean and variance would be for any given batch, right? It allows us to keep those numbers for further when we actually sample. Now, if it's not in training, that means you already have self.running mean and self.running var registered in the buffers, right? That's what self.registered buffer does. So if you're not in training, these are already there, right? So now that you have, mean and var values, you can actually normalize the batch itself. So you would say, x minus mean, you would minus the overall mean, which would come from self.running mean, or just come from the dimension itself, depending on whether you're training or not. And you divide it by square root of r. Yeah, this is just the basic this is just basic normalization in statistics. It basically brings it down to a normal value, right? Variance 1 and mean, that kind of stuff. So now that it's normalized and has a variance of 1, you know, now what you can do is you can allow the system to learn and scale the x norm values. So you can multiply with the gamma and add the beta, which allows the system to find some leeway into how much it has to scale for it to actually receive the proper value. So you're giving it some more space to learn patterns after you normalize it. So it's not just normalized values here. You allow it to denormalize it, but in a formal manner, so that you can scale it to a proper scale. And then there you have your forward, right? Same as last time, self.layer 1. Now, here what I removed, usually I would have the EMBs, right? Here I don't have the EMB. The reason is because when you actually sample, the viewing is different from when you actually train. So to allow for that distinction, you can specifically say how much you want to view it. Okay, so layer 1, you take h self weight, right? You batch normalize it, you put it into tan h, and you calculate layer 2, right? Easy enough. You put batch norm before tan h again because you want to reduce the saturation, and you return layer 2. This is basically your full model, right? Your forward tells the model that when you call the model and you give it the input, suppose that input x, what does it have to do? It would have to calculate layer 1. Then it would say self.batch norm. It would come over here and say, okay, we have input x, so we calculate the batch norm. And then it would, as soon as it calculates the batch norm, as soon as it uses the return value from here, whatever it returns is assigned to bn. Now layer 1 bn is torch.tan h of layer 1. So you would basically, okay, so here you would have to torch.tan h of bn, right? Because you're torch.tan hing the batch norm that you apply over here. Then layer 2 would be layer 1 bn, and then using the weights over there. And then you return layer 2, right? So that would be your overall output. This would be of shape 32 by 27. Okay, now we move on to the actual training loop. Learning rate we set as 0.01. Okay, that works. But we actually don't need this anymore. We don't need the learning rate over here. Okay, so first of all, we call the model. We call the whole class as model, and we call the MLP. And then you put into .train so that it knows that over here, it's going to do this instead of doing this, right? That's simple enough. So when you put .train, it does this part over here. Okay, now next part, the optimizer. Over here, we're using atom from torch.optim.atom, right? You have to remember this path. Okay, now how does model.parameters come here? We never really define parameters, but because we passed in nn.module, and for each of the parameters over here we call nn.parameter, it automatically knows what the parameters are. So model.parameters would go to MLP, and it would look at the nn.parameters, and it already knows these have requires grad is equals to true. So it automatically creates a list of all the parameters because you passed in nn.module and you called nn.parameters, right? That's the gist of it, and learning rate is the same as for learning rate 1e minus 3. Okay, so now this is the loop itself. So, k in 200,000, xy creates the batch, and then over here you model.c would refer to the c over here, right? Model.c, and then you index through it, you view the shape, you put the and then you call model x, right? You call model x, which would return layer 2 because of the forward, right? It would calculate the batch norm, and it would calculate the forward, and it would return layer 2. Now that's assigned to output, and then the loss is basically output and y. And you would calculate the loss, optimize that zero grad, same as before. It zeros all the gradients, so that when you go on to actually add the gradients, they don't add on top of each other, because gradients are aggregated unless you zero grad them. They keep on adding on top of each other. So after zero grad them over there, you lost that backward, which gives all the parameters their gradient values, and then optimizer.step is what actually changes these values within the weights and biases to alter the loss. So let's just call these two and see. Okay, so while this is happening, I will go on to explain this over here. Basically, this is for m in range 100, right? This is your sampling loop. Same as before, out is this over here. Context is this times block size. Now, while true, same as before, tensor. Now here, like we did over here, you would call model.cix, right? You take the C embedding from over here, and you pass in ix, which comes from over here. Okay, you view it differently. Again, this is exactly why we didn't put emb over here. The reason why we didn't put emb over here is so whenever you have to use this model again, you don't have to alter the model itself. Rather, you can put in your own individual values. Like you can put 32 here, but over here you can only apply one, so you cannot really define specifically uh, you know what shape you want. So it allows for some leeway, right, to actually input yourself. So now layer 2, you would get model h, right? So that would be the return statement from over here. And probs would same as softmax, call multinomial, and new. So yeah, nothing really changed there. And okay, so something has gone wrong, obviously. What has gone wrong? It was kind of a stupid mistake. Here instead of x, I think might have written h, right? And that kind of messed the whole system up. And then over here as well, I had xy, and then here instead of passing h, I was just passing in this x, and that messed up the whole thing. But yeah, as you can see, it works now, right? And that's the basic PyTorchification that we need, right? So the MLP, you call the inits, you define the different things, you call the batch norm, which helps to stabilize the variations. It helps to stabilize the batches that are coming into each of the models, so it doesn't explode or vanish, right? Forward is simple, the forward pass. Oh yeah, and I called model.train here. I went through the whole thing, right? Look for minor, errors, because that's what really gets you. For example, I'll take my example over here. I wrote h instead of x, so really be careful about those. Also here, remember to put model.eval, because that's what tells the model over here that okay, we're not using training, so we're going to have to use this, right? So remember to use these kind of things. And yeah, you can also increase the amount of epochs you have, add more layers, and so on and so forth. Okay, also, the reason why we do not apply batch norm to layer 2 is the same reason why we do not apply tan h to layer 2, because there's nowhere for layer 2 to go. Layer 2 is not going to go to a layer 3. If it did, then yes, we would add this batch norm. That way, that when it goes to layer 3, everything is normalized, so that when you apply tan h there between the layer 2 and layer 3, that layer 3 gets stable inputs. So that's why you didn't apply batch norm to layer 2, because layer 2 is not going anywhere. We're making our inference based on layer 2, so normalizing it doesn't really make any sense. Yeah. So yeah, that is our overall multi-layer perceptron. We looked at what to import, how to prepare this this text, creating the batch, ITOS, we looked at STOI, we looked at the different weights, we created our first, or maybe not the first, but we created our training loop, and then we created a sampling loop, and then we torchified everything. We added batch normalization to it, and we created this class, this model class, right? That does the heavy lifting for us, and that can be reused again and again. Okay, we called it, we trained it, and we sampled from it. Yeah, that should be it. I think that's all there is to the multi-layer perceptron. I still highly recommend watching Mr. Andre's video. I think he covers all of the detail in a much more effective way, and he definitely has more knowledge on this topic than I do, right? So I highly recommend watching his Make More series to actually get the better understanding for the reasons and the uh, the logic behind everything, right? He explains in much more detail as well. He also has like six or maybe five, six videos, which are each an hour to 2 hours long. So yeah, he really does go into a lot of detail, right? So I think that's it. Stay tuned, and I'll see you guys next video. Thank you.